For the reaction, aluminum oxide breaks up to 2 moles of aluminum plus 3/2 of a mole of oxygen. How many grams of aluminum could form when 7.44 times 10 to the 4 kilojoules of heat is used? Now, the first thing you might notice about this is how strange it is to have 3/2 of a mole of oxygen in a balanced equation. Usually, all the coefficients are integers. So why is it written this way? The answer to that is that this reaction is the reverse of the formation of aluminum oxide from its elements, aluminum and oxygen. And there's a whole table showing the heats of formation of various compounds. And the units, the enthalpy of those heats of formation are always in the units of kilojoules per 1 mole. Kilojoules per 1 mole. So this reaction is a decomposition. It's the reverse of the heat of formation of aluminum oxide. And therefore, the enthalpy has a positive sign. The heat of formation of aluminum oxide would be when aluminum, 2 moles of it, and 3/2 of a mole of oxygen combine to form 1 mole of aluminum oxide. And that enthalpy given off in the formation of aluminum oxide is what we call the enthalpy of formation. And of course, it's a very exothermic reaction when aluminum burns in oxygen to form aluminum oxide, minus 1676 kilojoules per mole of aluminum oxide. So this is the reverse of that reaction, a decomposition of aluminum oxide, and the sign of the enthalpy is changed. But here's the deal, it has to be per 1 mole, because that's how heats of formation are always given in a table, as kilojoules per 1 mole. So to maintain 1 mole of aluminum oxide, we have to use a fractional coefficient for the oxygen, 3/2 to be exact. So using fractional coefficients is okay when you're talking about the heat of formation of a compound or the heat of decomposition of a compound. It's okay to use fractional coefficients because the enthalpy that you look up in the table is going to be tied to 1 mole of whatever compound you're talking about. Now, the target of this reaction is grams, and the balanced equation here tells us that 2 moles of aluminum are produced for every 1676 kilojoules of heat energy consumed. That's what this balanced equation tells us, and what the enthalpy for the decomposition tells us. So there's your conversion factor, and now you're able to use that conversion factor if you set it up this way. 7.44 times 10 to the 4 kilojoules. That's the overall given amount of heat used. Now your conversion factor between kilojoules of energy for the reaction for every 2 moles of aluminum that are produced, and then a simple conversion of moles of aluminum into grams of aluminum, and that gives 2.4 times 10 to the 3 grams of aluminum. So here's another one. Water has a specific heat of 4.18 joules per gram delta degree C. And if you've got 160 joules are absorbed by 26 grams of water at a temperature of 24.4 degrees C, what is the new temperature of the water? What we can do is to solve for delta degrees C, put in our specific heat conversion factor, and then since water is absorbing heat, its new temperature should be greater than the original temperature. There's another way to do this too. We'll do it the algebraic way in a minute, but just watch how we've done it here. I've inverted my specific heat to give delta degree C in the numerator because I want to solve for delta degrees C, or the change in temperature. And then 1 gram in the numerator and 4.18 joules in the denominator. And I purposely inverted it to put delta degrees C in the numerator. Then what do? My given information is 26 grams of water. That'll cancel with my grams in the specific heat. And 160 joules in the numerator, that'll cancel with my 4.18 joules in the denominator. So what I get is grams canceling out, joules canceling out, and I end up with 1.47 delta degrees C. That's a change in temperature. The original temperature was 24.4. But it's absorbing heat, and therefore this change in temperature is going to be added to the 24.4 to give me my new temperature, 25.9 degrees C. So that's one way of doing it, by just canceling out units to end up with the unit that you want, in this case delta degrees C, and then applying that to the original temperature. Another way to do this is algebraically. What we do there is let x equal the new temperature, and then we set it up the usual way, 4.18 joules per gram delta degrees C. Multiply that by the grams, 26 grams. And we write the delta degrees C as a little algebraic expression where x is the new temperature, and we know that x is going to be a larger number than 24.4 because it's absorbing heat. That's why we wouldn't write 24.4 minus x. It has to be a positive number that we end up with here in the delta degrees C part. So that's going to be x, the new temperature, minus 24.4. And all of that has to equal 160 joules. And so, as I said, we subtract x because x, the new temperature, will be greater than the original temperature. Here it is, solving for x. We get 108.68. X minus 2651.8 equals 160. And moving that all around, we get our new temperature that way, solving for x. So you can solve this either way. I'm partial to the algebraic solution to it, but you can solve it any which way. Okay, now a bomb calorimeter is a device used to measure the change in energy because it's a constant volume system. And what you do is you put a little of your sample in here. You know, this is how they figure out on your Rice Krispies how many calories are in an ounce of Rice Krispies or whatever. They use a device just like this. They put your Rice Krispies in this little cup right here. Then they put a lot of pure oxygen gas all around it so it'll burn completely. And they take this and they lower it. It's got a little fuse in there that will ignite the Rice Krispies or whatever. The temperature of the water before you press the button is taken, then you push the button, the Rice Krispie burns, heat is given off, and the heat flows into the calorimeter. The water stirred around, and you can keep track of the temperature as it rises. So here's one. A 20-gram piece of calcium at 25 degrees is dropped into a calorimeter holding 100 grams of 9 molar HCl. And the specific heat is there, 1.01, the density 1.0 gram per milliliter at 25 degrees. The reaction is calcium plus 2 moles of HCl yields hydrogen gas and calcium chloride and heat. The temperature in the calorimeter then rises to 73 degrees. So what's the enthalpy in kilocalories per mole for this reaction? Okay, so our target is kilocalories per mole of calcium. And we use the law of conservation of energy. The heat lost by the reaction is gained by the calorimeter. So we use the mass of the HCl, the change in temperature, and the specific heat to calculate this energy that was lost by the reaction and taken on or absorbed by the calorimeter. And then we use the atomic weight of calcium to convert grams of calcium to moles of calcium, and then we can pretty much figure out the kilocalories per mole for this reaction. Okay, you ready? Here we go. 1.01 calories per gram delta degree C, the specific heat of the calorimeter, times 100 grams, which would be the mass of the HCl solution, times the change in temperature, 73 minus 25. That's equal to 4848 calories, or 4.85 kilocalories. And 20 grams of calcium divided by 40 is a half a mole of calcium. So now we have the kilocalories for this reaction. We have the moles of calcium that we used, 0.5 moles, and divide one by the other, and we get 9.70 kilocalories per mole as the enthalpy for this reaction. There's another question that you frequently get. 2 kilogram iron horseshoe heated to 800 degrees C, and it's dropped into a pot of water. And then the water has a mass of 1.3 kilograms at 22 degrees C. Calculate the new temperature of the water and the horseshoe. And the specific heat of water is given to us, and the specific heat of the iron is given to us. And we assume no heat lost to the pot or the surroundings. So here's our plan of attack. The concept is, again, heat energy lost by the horseshoe is gained by the water. So I'm going to let Z equal the new temperature of the water and the horseshoe. I'm going to solve this algebraically, and it would look something like this. 0.45 joules per gram delta degree C times 500 grams, and that's the mass of the horseshoe, and the specific heat of the iron of the horseshoe, times 800 minus Z would be the change in temperature. And we do it this way because Z, the new temperature, is less than 800. The horseshoe's cooling down. And we always want a positive for this change in temperature. So it's going to be 800 minus Z equals the joules lost by the horseshoe. And as far as the joules gained by the water, that's 4.184 joules per gram degree C, 1,300 grams of water times Z minus 22. Why is it Z minus 22? Because now the new temperature, Z, is going to be greater than the starting temperature of the water, which was 22. So to have a positive change in temperature, it's going to be Z minus 22. Put those together, and that's the joules gained by the water. So we make the two reactions equal to each other because the joules lost by the horseshoe has to equal the joules gained by the water. And now we have an algebraic expression, and all we have to do is solve that equation for Z. Heat lost equals heat gained. So it's going to be something like this. We solve it, Z, and we get 52.9, the new temperature. Now, in your book, you'll see this table of standard enthalpies of formation. Delta H, subscript F, enthalpies of formation. And these are the energies that are released or absorbed when the compound is formed from its elements. The elements arbitrarily are given a enthalpy of 0. If it's a pure element in its standard state, it's arbitrarily given an enthalpy of 0. And when elements combine to form compounds, the heat that is absorbed or released becomes the heat of formation of that compound. So for example, for atomic bromine, atoms of bromine as a gas. Now that is not the standard state of the element bromine. The standard state of the element bromine is in the liquid state as a diatomic molecule, Br2. And that has an enthalpy of formation of 0, arbitrarily by the rules. But in forming atomic bromine as a gas, that requires energy to break up the Br2 and to vaporize it from the liquid to the gas. Both of those require energy, and the energy is 111.9 kilojoules per mole. Okay? Or HBr is a gas as well, hydrogen bromide. Now, when hydrogen and bromine get together to form hydrogen bromide, energy is released, specifically minus 36.3 kilojoules per mole. So that's where these enthalpies of formation come from. Literally, it's the heat of formation of the compound. Because enthalpies are a state function, you can add and subtract them. We already talked about that. It is independent of the path. And therefore, by adding and subtracting enthalpies of formation, you can calculate the enthalpy for an entire reaction. Here's a reaction. 2 moles of sodium plus 2 moles of water yield 2 moles of sodium hydroxide as a solid plus 1 mole of hydrogen gas. Now, it's important to note the phase of these things because, for example, sodium as a solid is the stable elemental form of sodium, so we know its enthalpy is going to be 0. If it were sodium as a liquid, we'd have to look it up in the table because it wouldn't be 0. It has to be in its stable phase. Water is, of course, a compound. Therefore, it has an enthalpy of formation. And this is marked as liquid water, not gaseous water, not solid water, but liquid water. And liquid water has an enthalpy of formation of minus 68 kilocalories per mole. On the other side, the sodium hydroxide is a compound. In this case, it's a solid, and its enthalpy of formation is minus 102 kilocalories per mole. And hydrogen, as a gas, has an enthalpy of formation of 0. Now, how do we do it? What we do is continue the tradition of finding a delta by the sum of the final conditions minus the sum of the initial conditions. And by that we mean the sum of the enthalpies of formation of the products minus the sum of the enthalpy of formation of the reactants. That would be final minus initial. So in this case, 2 moles of sodium hydroxide at minus 102 kilocalories per mole. So that's the sum of the heats of formation of the product, minus 2 times minus 68. Minus 68 is the kilocalories per mole of the heat of formation of water. Multiply by 2 because there's 2 moles of water, and we get minus 68 kilocalories as the answer to this. The other nifty thing you can do with the enthalpies of reactions, after you find the enthalpy of a reaction or are given the enthalpy of a reaction, is that you can modify the equations or the reaction equation so that you can add up specific reactions to give the enthalpy of another reaction that hasn't been given to you. As an example, let's use this one. We want the enthalpy of the reaction PCl3 as a liquid plus Cl2 as a gas yields PCl5. Okay? So that is our target. And we're given two reactions. We're given P4 as a solid plus 6 moles of chlorine gas yields 4 moles of PCl3 as a liquid. And we're told what the enthalpy for this reaction is, minus 1280 kilojoules. And then we're given another reaction, P4 as a solid, plus 10 Cl2 as a gas yields 4 PCl5 as a solid, and the enthalpy for that is minus 1774 kilojoules. Now, there's a very good way to do these that makes it really easy if you're meticulous about identifying your target. What do you want to end up with? What reaction do you want to end up with? In this case, it's spelled out in the first line. What we want to end up with is the enthalpy for the reaction PCl3 plus Cl2 yields PCl5. And these are the two components that we're going to tweak so that when we add them up, we can also add the enthalpies of the reactions and end up with the enthalpy of the reaction that we're trying to find. Now, this is how you do it. You take a look at your target. You see PCl3 is a reactant in the target. In one of your given equations here, you look for PCl3. And here it is in this first one that was given. But you see that the PCl3 is on the product side, but in your target it's on the reagent side, right? So what you're going to do is you're going to flip this reaction where the reactant becomes the product and the products become the reactant. So when you flip it, you end up with 4 PCl3 yields 6 Cl2 plus P4. But note also what you've done to the enthalpy. You've changed its sign. It was minus 1280. Now it becomes plus 1280. By flipping a reaction, you change the sign of the enthalpy. Why did we flip it? Because in our target, PCl3 is on the reagent side. And in our given reaction, it's on the product side. So we flip it around to put PCl3 on the reagent side. And in doing that, we change the sign of the enthalpy. Okay, what about this reaction? P4 plus 10 Cl2 yields 4 PCl5. Well, take a look at our reaction. We have PCl5 as a product in our target. And over here we have PCl5 as a product in our given reaction. So I am not going to flip this one. I am merely going to take this one, move it down. It's the same reaction as before. You should see that P4 is not in our target, but it is in each one of our given reactions. You see that? We can cancel out the P4. If we have equal moles of P4 as a product and as a reagent, we can essentially subtract them out from each other by adding these two reactions. So what I'm going to do is add these two reactions, and in doing so I'm going to add the heats of each one of the reactions. I'm going to cancel out the P4 when I add them, and I'm going to lessen the amount of Cl2. I have 6 moles of Cl2 in one reaction and 10 moles of Cl2 in the other, on the other side, on the reagent side. The 6 Cl2 is on the product side. So now I can subtract 6 Cl2 from both sides and end up with 4 Cl2. So when I add these all up, I'm going to end up with 4 PCl3 plus 4 Cl2 yields 4 PCl5. Okay, we're almost there. We're almost there. Our target doesn't have 4 moles and 4 moles and 4 moles. It has just 1 mole of PCl3, 1 mole of Cl2, and 1 mole of PCl5. So if I multiply every coefficient, every term by 1/4 or a quarter, I will convert the 4 moles of each compound to 1 mole of each compound. And in doing that, I also have to divide the minus 494 kilojoules by 4, multiply it by a quarter to get the answer to the problem, minus 123.5. So our target reaction has an enthalpy of minus 123.5 kilojoules. Okay, here's another one. What I'd like you to do is to try this one yourself. Okay, here's your target reaction. Here are the two reactions that you're given with their enthalpies. Turn off the playback. See if you can do this by manipulating the given reactions so you end up with a target. Okay, let's analyze this again. We have tungsten trioxide, WO3, plus 3 hydrogens yields tungsten as a solid, plus 3 water. We look at our first given reaction, we see tungsten trioxide on the product side. On our target, it's on the reagent side. So the first thing I'm going to do is flip that first reaction, flip it right over, and now I have tungsten trioxide as a reagent. And of course, I've changed the sign of my enthalpy, just like we did in the last example. What about the H2 plus 1/2? O2 yields H2O. Let's take a look. Well, first of all, water is on the correct side. It's on the product side, and in the target, it's on the product side. But you notice we have 3 moles of water on our target, and only 1 mole of water in the given reaction, also on the product side. So it seems to me that we're going to have to multiply each one of these terms by 3, and the enthalpy as well, to get to the point where we have 3 moles of water on the product side. So that's what I'll do next. I'll multiply every term by 3. The 1/2 mole of oxygen becomes 3/2 of a mole of oxygen, then 3 moles of water, and of course with our enthalpy, it becomes minus 238.92 times 3. So you get minus 716.76 for this reaction. And now when I add them up, I get our target reaction, and I get the enthalpy for that, plus 125.94 kilojoules.